then I'll start, I guess. Okay. So, hello everyone. I'm David Spataro from the FTX group at DESI in Hamburg, Germany. And I'm very happy to be here and to have this great opportunity to talk about how we do track reconstruction at LUXE with quantum algorithms. Let me begin with introducing LUXE, which is short for Laser and X-FEL Experiment. LUXE is a proposed new experiment at DESI and the European XFEL. The XFEL is a free electron laser, and it will be crossed with a high power laser to study the transition far into the non-perturbative regime of QED for the first time. The map shows where the LUXE is located. It's between the DESI area and the end of the beamline of the XFEL. If you want to know more about LUXE, there's a website about the experiment and also about a conceptual design report. I would also like to mention our past results for track reconstruction at LUXE with quantum algorithms on this link here. First, I would like to provide a small overview of the setup and to talk about what we want to observe at LUXE. So the 16.5 GeV electron beam from the XFEL or Bremsstrahlung photon beam in a possible additional setup is crossed with a powerful laser. And LUXE consists of basically two phases. And in the second phase, the laser is planned to be upgraded to 350 terawatt. And the two processes of special interest are one is the nonlinear Compton scattering or multiphoton scattering, and that's scattering of multiple low energy photons, which are given by an intense electric field into a high energy photon. And this is during an interaction with a charged particle. And the second process is bright Wheeler pair production. And in this process, matter is created from the collision of at least two photons. So an electron-positron pair. And this process is shown in the figure on the right. And our track reconstruction algorithms are used to reconstruct these positrons. The number of these created electron-positron pairs depends on the existing electric field strength. And that's why above a certain threshold, which is called the Schwinger limit, novel phenomena can be observed. In LUXE, we want to scan the classical non-linearity parameter Xi to investigate the transition from the perturbative into the non-perturbative regime of QED. And Xi is driven by the instantaneous laser field strength and the ratio of the instantaneous laser field strength and the Schwinger limit. So when Xi is of the order of 1 or higher, so in about this region, then there's a significant difference in the number of created positron and electron pairs between the prediction of the non-perturbative QED and the perturbative QED. And to test this hypothesis, it is crucial to reconstruct tracks with both a high efficiency and a low fake rate. The tracks are reconstructed from hits recorded by our positron tracking system. The electron-positron pairs which are created are separated by a strong magnet and then guided to the pixel tracker and the calorimeter. And the detector is based on the Alpine silicon pixel sensor and it consists of 9 chips on each stave. These are these greenish rectangles which partly overlap in the setup. As a starting point, we are using a simplified simulation, and that's because we want to control and study the impact of physics processes and of the detector geometry on the performance of the reconstruction algorithms we are using. So a modified and also a bit simpler geometry is displayed in the figure on the right. The gray rectangles are the detector layers, and the red tiny red rectangles are the hits on the detector, and also some tracks shown in green. As an input, the simplified simulation takes events created from ptarmigan. Ptarmigan is short here for ponderomotive trajectories and radiation emission. And this ptarmigan just simulates what's happening at the interaction point at LUXE. But the simplified simulation can also be used to get a rough idea about the detector occupancy. And LUXE, we are expecting up to approximately 1 million positrons per event, but this is depending on the Xi value. And we also expect a region with slightly increased occupancy for these events. And in the future, we will explicitly look at this region with our quantum algorithm. We're wondering if there could be an advantage in comparison to conventional track reconstruction techniques, but we have also strategies to handle scenarios for more than the roughly 10,000 positrons in this example plot. I continue now with an overview of the approaches we are using, and we compare 3 different ones. First, a quantum algorithm, then a graph neural network, and also a conventional track reconstruction method. Let me start from the interaction point of LUXE. Since we do not have experimental data, we employ the simulated data from ptarmigan, and we process these information with the simplified simulation, and as a result, we simply get the hits on the detector layer. And in the next step, we group these hits from consecutive layers to doublets and combine into triplets. But holes are not allowed, meaning skipping layers in between to create the triplets or doublets is forbidden. And the decision if a doublet or a triplet is kept in this pre-selection process is just based on angles between these doublets and the position of the hits on the detector layer. So now I'm going to present the 3 approaches, and 2 of them rely on the triplet information, and 1 of them just relies on this doublet level. So for conventional tracking, we are using the ACTS tracking library. We also use it as kind of a benchmark for our other approaches. For seeding, we are using the first 3 layers, and that's quite similar to the triplet preselection. So the initial estimate of the track parameters from the seed is then used to predict the next hit, and this is updated progressively. The measurement search is performed then at the same time as the fit. Graph neural networks are great at modeling interactions or relations of objects. And
David, wait a second, please. We lost the screen.
Oh, you don't have to.
Oh, sorry.
You don't have to unmute.
No, we were muted. We were muted, and we
lost
you.
What worked last time was to shut things down. So give me a minute. Sorry. Oh shoot! Sorry, just disconnect this.
You need the mouse?
I will. Yeah. Sorry, it's going to take 5 minutes.
Yeah.
I hope I don't turn the lights off in the room. If I do, sorry.
Yeah, they're shutting this off.
Yeah, no, now I've shut everything down. So, this one come back up.
It's strange, just showing noise, like analog noise.
Yeah, yeah. And it's just different.
And the projector loses the scene.
Yeah.
I wonder if we should restart the projector instead of restarting the computer. That switch sources of things like that.
That might have been a better solution. Sources. That'll be the next try. If we have to do this again.
Do you have the code to get into the advanced settings? I don't know about that again.
No, but I guess we could call and get it today. I would actually call.
Okay. I wouldn't sit under there.
Look at that. It's working.
But I think now we're not on, we're still on Zoom. Oh, awesome. Okay. I hope it continues getting brighter.
So can you hear us now?
Yes.
That's a good sign. Give us 30 seconds until the screen comes back. I think we're good, right?
Right. Great. Hopefully the frequency is not 1 per hour.
Yes.
Are we muted?
David, we are ready to go whenever you want.
Okay, great. When exactly did I lost you, or vice versa? At the start of the slide, or?
No, you.
Why don't you reboot the slide? Yes, you were talking about ACTS and now you were using it as a benchmark. That's the last.
Ah, okay, right. Okay, right. Yeah, that's fine. And I can go on with the GNN. Great. Okay. So I'll continue. Graph neural networks are great at modeling interactions or relations of objects. And that's the reason why it's one of our choices for the reconstruction task. The difference to the two other approaches that only doublet-like information is encoded. But for the graph neural network, this is called a segment. I put some links on the slide where the approach is explained. There's also the extension XR-TrackX. I recall there were also some presentations about it on Tuesday, I guess. And also there's a hybrid quantum classical version, Q-TrackX, which we want to use in the future too. For the quantum algorithm approach, we are using a formulation called QUBO, which is short for quadratic unconstrained binary optimization. And it is different, but equivalent formulation of the Ising model. So what we do is we are basically building a Hamiltonian in which we encode the relations between our triplets. This approach is motivated by a pattern recognition algorithm for quantum annealers, for which I put the archive link here. So before we actually can use quantum computing to solve a problem, a suiting problem formulation is needed, and this is where the qubit joins again. Information about triplets is encoded in two values. A connection term, which is modeling on how different triplets interact with each other. So if they have no shared hit, then we just apply a value 0. And if they are in conflict with each other, we punish them with an integer 1. But if they form a valid track, may it result or in a fake or a real track, the connection is calculated based on the angles of the doublets. We can also assign a quality value to each triplet if we want to, as a reward if the triplet is straight, and as a punishment if that's not the case. So if we minimize the objective, only true triplets in this picture shown on the right side will be chosen. So this will result in either the two triplets for track I overlapping will survive, or the two triplets which form track B will survive, but not both. And to minimize the objective with the help of a quantum computer, it has to be translated into an Ising Hamiltonian. That's because for the objectives, the Ti are either 0 or 1, whereas in the Ising model, these sigmas have the values -1 and 1 corresponding to spins, for example. And a candidate for such an algorithm to minimize this objective is VQE. But before discussing this method, I would like to provide a minimal overview about quantum computing. The first question that probably arises is, why do we want to use quantum computing? And the answer to that is, we believe that for some problems or tasks, quantum computing might be advantageous. For instance, factoring, cryptography, or also optimization problems. Let's start with the qubit as the smallest computing unit. It can be seen as a two-level quantum system. So instead of having just two states, 1 and 0, like a classical bit, it can be in a superposition of these states. And to manipulate qubits into the states of superposition, unitary operators or gates are used for this. One can imagine that a qubit is a vector inside a sphere, and that the gates are rotating these vectors around the center of the sphere. A quantum circuit consists, similar to classical circuit, of an initialization. There are gates and there are measurements. And in this example, these single qubit gates are parametrized gates. And that means that a rotation of the qubit vector is performed with respect to a parameter theta in this case. The C0 gate here is an example for a 2-qubit gate. What it does is it flips the second bit only if the first bit is in state 1. And the classical analog would be a reversible XOR gate. And this gate is often used in combination with a parametrized gate to create entanglements. And entanglement is a particularly unique feature in quantum mechanics, and it is one of the key features of quantum computing. Now coming to VQE. VQE is short for variational quantum eigensolver, and it's actually a hybrid quantum classical algorithm in which a quantum device is used for the energy evaluation, whereas a classical optimizer is used to update these parameters theta. And the idea of VQE is based on the method of on the variational method of quantum mechanics. So there's like a trial wave function chosen, and one varies a set of parameters to find the lowest expectation value of the energy. And for track reconstruction, we can identify the lowest energy of the system with an optimal result in maybe terms of efficiency and fake rate for tracks. But for VQE, a dedicated quantum circuit has to be chosen. And in this quantum circuit, there are these parameterized gates. And basically the whole purpose of this algorithm is to find an optimal set of these parameters. So after each iteration, the energy value is calculated and the classical optimizer then is updating the parameters, and this whole procedure is repeated until the result converges. When choosing an ansatz circuit, it has to be considered that we only have access to quantum computers with a low number of qubits at the moment. And when we use these quantum computers for calculations, the results are rather noisy. And therefore, it is essential that we choose a hardware efficient ansatz. So we have to make sure that the number of the parameters which we're using is sufficient for the calculation, and that the circuit itself consists of a minimum of gates, so to keep the noise level low. And a good starting point for this ansatz choice is to repeat these blocks of rotational gates and entanglements until a good expressivity of the circuit is given. And that means it is possible to find the ground state of the Hamiltonian. And another thing to consider is also the topology of the quantum device. The ansatz circuit has to be mapped to the device. So an example is shown here. And it is important to identify a set of qubits here which resemble the qubit relations of the ansatz circuit in terms of these two qubit gates. So for example, in the given ansatz, there are 3 qubits and they are entangled with each other in like a circle. So qubit 1 is entangled with qubit 2, 2 with 3, and 3 with 1 again. So we need to find this structure here, but unfortunately that does not work on this device. So we have to swap around gates a bit to make it work. And this is, this is one of many challenges, but there are also workarounds and solutions for these problems. Like there's an optimization algorithm for the mapping, and for the noise, there are things like error mitigation and or error correction techniques. For the result of this task, however, we are using the Qiskit package from IBM with an ideal simulation. This means we have no noise and no mapping has to be done. But I want you to show one result on an actual device and how this might look like. For this, we formulated a Hamiltonian for 5 triplets stemming from 2 particle tracks and used the IBM Santiago device. To compare the result, we did the same thing for an ideal simulation. And we compared these results. And you can see that the correct solution in this state is also favored in terms of probability on the real device. So we got a correct solution. Great. Let's also talk about computational feasibility. If we would like to process a whole event at LUXE with a quantum computer now, we have to introduce a new concept to handle large Hamiltonians. And the reason is that if you're looking at one event with roughly 10,500 particles, we end up with 150,000 triplets. So we would need the same amount of qubits for it for a real device. But this number is totally out of reach at the moment. But to prove the concept, we can use a smaller number of particles. So we restrict ourselves to 500 and 1000 particles with the highest energy within the event. And these are the tracks or particles which are closest to the beam lines. This is shown here in this black oval. But even the simulation of small quantum devices takes a considerable time on a classical computer. This is why we also choose a fixed size of 7 qubits for now, since there's also real devices at IBM, so we can later compare these results. But there's no chance to fit these 500 particles into a 7-qubit device. So the Hamiltonian has to be partitioned into smaller pieces, and these smaller pieces we call subqubits.
David, you have 4 minutes.
Yes, that's fine. The strategy for the subqubit is the following. We are looking into the whole qubit and guess an initial binary vector representing the solution. We go through every triplet and check how the energy would change if we would flip the bit. And this energy change, or impact we call it, is used to sort the triplet list. Then we take the first 7 triplets of the sorted list and put them together into the subqubit, and then we solve it. And then we proceed with the next 7 triplets and so on. And this whole procedure is then repeated until we again reach the convergence of the energy. So to measure the performance of the track reconstruction for the different approaches, we are using efficiency and fake rate, and we define a correct track as all 4 hits match to the same generated particle. We compare a conventional track reconstruction with a combinatorial Kalman filter, a graph neural network, and a quantum approach for different psi values. For the QO, there's also an analytical solution by diagonalizing the Hamiltonian, and that can be also used to evaluate the performance of VQE on the subqubit level, and also it can be used to evaluate the performance of the global optimization algorithm. And this diagonalization method, we call it eigensolver in the results slides. And simulation with noise and the performance on a real quantum device were only tested on a smaller scale. So first, I would like to present the results for 500 tracks for phase 0 of LUXE. And we can see that the conventional tracking is some kind of benchmark for us, but we are coming close to it with the GNN in general, and for the quantum approach, at least for Xi 4 and 5, in terms of efficiency. For the fake rate, the quantum approach with both eigensolver and VQE shows a significantly higher fake rate than the GNN and the conventional tracking. When comparing the eigensolver and VQE, red and the green line, it seems that the modeling of our quantum circuit and optimizer is already quite good, as both results only differ by a small amount. And I would like to stress that we are only at the start of exploring what we can achieve. And we already know that tweaking the parameters of the QO has a huge effect on the performance, and that's what we are currently working on. And also we are restricted by the subqubit size, which makes us rather find local minima instead of the ground state of the Hamiltonian. So for example, increasing the subqubit size actually helps a lot. So by increasing the size from 7 to 16 qubits, we gain like 10% of efficiency. But this comes also with a bit higher fake rate. But we can also, we are also investigating the choice of the optimizer and the ansatz circuit. So this is just a past result we had for phase 1, and it shows what a great difference a suitable optimizer can make. We just switched from the Kobila optimizer to the NFT, and it seems that we are then very close to the VQE, which is kind of the maximum efficiency we can reach. Another possibility to improve the results for BQE, so that the performance comes closer or even matches the eigensolver, is to vary the entanglement structure. I would rather not go into much detail, but just point out that the way the qubits are entangled with each other may have a non-negligible influence. I will now end with a summary and outlook. So our conclusions is that the track reconstruction with a hybrid quantum classical algorithm is possible and has a great potential. That's because quantum computing is great at complex combinatorial tasks, and we believe it might be advantage for it. We encountered some limiting factors that we could not work around entirely for the moment. And one of them is the size and the availability of the quantum device. But we are confident to match with GNN, the graph neural network, and conventional tracking in the future because we identify a lot of parameters on which we can improve. So my last slide contains a brief overview on what we've done so far and what we need to improve or what to investigate in the future. At the moment, we have a working framework. We can solve small qubits even on a real device, and we are quite happy with our optimizer. But we know that the global optimization algorithm, the subqubit approach, needs to be refined. For the future, we also will include noise and need therefore error mitigation techniques. And we also have to improve how we set up the parameters for the qubit Hamiltonian. And most of the challenges after that will have a focus on real devices like error correction or mapping these Hamiltonians efficiently to a real device. So that's all for me. Thank you very much.
Thanks, David, for the. Thanks, David. Very, very instructional talk. And sorry about the little hiccup. I'm not so little.
No problem.
So questions, actually, let's start from Zoom. Questions from Zoom. Hands in the room. Go ahead, and everyone, reminder, please say your name before asking the question.
Yeah. Hello, this is Michel. I found it very interesting. I have very little knowledge about quantum tracking on quantum computers, but I think the study you linked was using a dedicated quantum annealer D-wave, while you're using a different system. And I was a bit wondering how much the effect of this is, or is this negligible at the moment?
Yes, hello. Okay. So yes, you're right.
Please mute if you are not active. Just hang on for a second.
Okay, now it's muted. Okay. Sorry, Michel. Yes, you're right. They used a quantum annealer, I think, with like 1,000 qubits, and I'm not sure how it would have an effect on our results if we had the same possibilities. But yeah, we don't have access to a quantum device with 1,000 qubits, so I guess that's the main difference. Does that answer your question, or?
Yes. Yeah. Essentially, I was just wondering if going to a system which basically dedicated to doing the task you seem to be doing would improve. I mean, would basically reduce your limitations that you have on the number of qubits. But as you said, you didn't have the possibility to test it, so I guess it's not so clear to say.
Yeah.
More comments, questions?
I have one problem.
Go for it.
This is Andy. Hello. So how do you see the interpretability of your results? I mean, if you use a classical algorithm, you get an error estimate out that the least square estimator gives you on a track fit. Yeah, so you can interpret it basically as the best option in a least square estimator. If you want to quote anyhow your resolutions or something, you need to sort of have a interpretation of your error. How would you go with that on a quantum device? Or is this a stupid question? I don't know.
No, no, of course not. Let me think a few seconds about it. So I'm not sure in what direction your question would lead. Do you mean if there's error in the calculation itself when using a quantum device, or?
Yeah, in general, if you use a classical algorithm, let's say the track fit, then your assumption to find the parameters is the solution of a least square estimator. So you basically assume you have a Gaussian probability density function, and you find the minimum giving that. Yeah, it has its limitations, but it gives you at the end of the outcome something which you can interpret as a chi-square probability. Now, if you have a quantum-based algorithm as a solver for this, I never understood how you interpret your uncertainty in such a system.
Yeah, this is a good question, because we are not using this chi-squared, but we are using like an energy value, right? And you mean how to calculate the error on that, right?
Right, or you use it downstream. You use your reconstructed object downstream for, let's assume you found all the tracks and fitted them in an annealing scheme with a quantum device, and then you use them later on in a vertexing setup, so a vertex fitter. Then you have an assigned error to each track, which, if it comes out of a classical algorithm, you take it from a least square estimate and say, like, that's my Gaussian error that I assume to be normally distributed because I've been using a least square estimation technique. That's why I can use it such in a vertexing setup. Now, my question is, how do you do that on a quantum solver? Or is something we have to answer along later on in your timeline? This is also.
So we later apply a classical fit. So maybe that's the answer to it. So the choice of the triplets is done via the quantum computing, but the actual track fitting is then done in a classical way.
Yeah, I mean, he's doing track finding,
yeah.
Right? Yeah. One final question, if I may, David. On your slide 17, you have you're comparing a simulation to running actually on 5 qubits on an IBM Q, right? So yes. This ideal simulation is an ideal simulation of the IBM Q, or is an ideal simulation like a classical cube optimizer running on a classical computer?
I think it's just just a simulation without noise and so on. So it kind of simulates these VQE algorithm, but yeah.
But so you're simulating the VQE algorithm. You're not simulating the classical binary optimizer. Okay. because we're running on the annealer. You could do classical annealing or quantum annealing. Oh, not again. Okay. David, thanks again. Because we lost again our screen. So let's thank the speaker again. Let's